Welcome to the Optical Communication course. Today we will go for the MCQ on model 4, 5 and 6. Now question 1. Optical power output of illumination source measured in BAM, beam width, radiance, acceptance angle or numerical aperture. Now we can, if you see that the answer for this particular question, power output is in terms of a light. That's why it output of illuminated source measured in a radiance here. So that's why option B is correct. Next one, the refractive index of the medium separating the source and fiber is different from refractive index of fiber core. Then for perpendicular fiber in faces, the power coupled into the fiber reduces by a factor called as, because that refractive index is depending upon that whatever the material we are using. And then that refractive index we are separating for the different fiber because it is a power coupled to the fiber, and according to that the power coupled to the fiber is reduces by the factor of a reflectivity, or we can say that by the factor of a fractional reflection coefficient. So we can use that the way that what will be the a coefficient, whether it will be a reflectivity or frictional coefficient. So if you see that, so both the answer for this question number 2 is correct one. Okay, that is about, we can say that a frictional reflection coefficient, as well as we can say that both are correct here. Right, so that's why that answer is about a C is correct. Now next about, if the source emitting area, right, and if you consider that if the source emitting area is larger than the fiber core area, then the resulting optical power coupled into the fiber is minimum, maximum, same, or all of the above. Now you can see that if the source emitting area is larger than the fiber core area, because what we are saying that the emitting area is larger. So if that emitting area is larger than the core area, so the maximum power will be coupled to the optical fiber. So that's why that option is B is correct. Now next about, in a fiber to fiber joint, a permanent bond is referred to as dash dash, whereas a demountable joint is known as, whether it is collector or splice. Permanent joint is a splice, and demountable joint it is a coupler. So that's why the option B is a correct one. Next, the optical power that can be coupled from one fiber to another fiber is limited by. We are saying that the power is coupling from one fiber to the another fiber. So in that case, there is no role of a numerical aperture or ray theory of a light. It is the role of a number of modes. That's why that number of modes, according to the number of modes, that power couple will be increased or decreased. So that's why optical power that can couple from one fiber to another fiber, it is limited to the number of modes that propagate in each fiber. That is option A is correct. Then the fiber to fiber coupling efficiency. Now the fiber to fiber coupling efficiency, again it is depending upon that what will be the number of modes are there. So that's why that efficiency, if we consider it is in terms of the ratio, then it is a common mode volume to the number of modes emitting in the fiber. So that's why option B is the correct one. Then a 7, an optical receiver consists of, now the receiver, it has a detector, it has an amplifier, it has a signal processing circuit. So that's why that option D is a correct, all of the above, because optical receiver has a all of the component there. Next, in optical fiber communication, the receiver bandwidth depends on that receiver bandwidth. If we consider that the receiver bandwidth, so it is depending upon, generally we say that a rate of transmission rate is there. But at the end, we have the receiver. So if you see the receiver has all other components. That is, it has the detector, it has a filter, it has an amplifier. So that's why bandwidth is depending upon those components. So mostly, if you see that here at a detector, so that bandwidth affects by the filter. So that's why the low pass filter in the receiver, so that will affect your bandwidth. So that's why the last option, that D, is a correct one. Next one, the signal to noise ratio degraded by thermal noise in the receiver electronics can be suppressed by. So if you consider that whatever the signal to noise ratio is there, and that ratio uh, degraded by the whatever the thermal noise. Now what about the thermal noise? Thermal noise is a property. It is arises at the receiver. Now if we have the a receiver has a amplifier or a load resistors at a receiver, in that case there will be a thermal noise arises. So now we can say that the thermal noise is there because there is a amplifier. So now an optical amplifier plays after photodiode or an plays before. So because the degradation of a signal to noise ratio is there in the receiver electronics can be suppressed by the whichever the optical amplifier if you place before the photodiode. So that's why the signal to noise ratio will be increased. So that's why you can say that that option B, okay, it is a correct one. Then thermal noise arises in the electronic device because there is a random motion of electrons in a conductor, that is a resistor. Okay, not a discrete current nature of a current flow in the device. It is a random motion of the electrons in the a conductor. So that's why that option B is the correct. Then a thermal noise arises at the photodetector. If you see that the thermal noise, it is nothing but a load resistors, and again that noise is arises because of that amplifier. That's why from the photodetector load resistors as well as from the amplifier electronics. So there will be a noise because thermal noise will be arises because of those. But short noise, if you consider that, it is in a photodetector itself. Then a surface emitting LEDs are characterized by what will be your pattern. So it is a Lambertian output pattern. Lambertian output pattern means what? So from a observer point of view, it is seen that a device or that particular object is radiate a signal in all directions. But if you consider the output pattern in terms of intensity, so it's radiate a signal in one direction. So we could not say it is a unidirectional. That is to be measured in a pattern. That pattern is called as a Lambertian output pattern. And omnidirectional radiation pattern means what? It is a radiating signal in all the directions in a one place. Okay, so that is a difference in a Lambertian output pattern and a omnidirectional. So our answer will be a Lambertian output pattern. Next, in optical communication, two identically sized sources operating at a different wavelength but having identical radiance will launch dash optical power into the same fiber. Now, if you consider that there are the two identical fiber, so according to that two identical fiber, so they will launch a power the same fiber that will be equal one because the identical fibers are there. Next, if the emitter area of the source is smaller than the core area, then the device placed between the source to fiber to improve the power coupling efficiency. So now which device? We need to use not a connector, not a coupler, need to use a lens. That is called as a micro lens. So micro lens means what? It will increase the it will increase the source size or it will decrease the source size, and it will fit your output to the your core of a fiber, optical fiber core. So that's why that coupling efficiency will be improved there. Next, in fiber to fiber joints, the losses depends on. Now, if you consider that the losses at a fiber to fiber joint, that is a distributions in terms of a power. So that's why the input power distribution to the joint. Then the length of the fiber between the optical source and the joint, that will be decreases there. The geometrical and waveguide characteristics of the two fiber ends at the joint. So that's why all of the options will be correct. That's why the D is there. Then optical power received at the photodetector depends on amount of light coupled into the fiber, the loss occurring, in the fiber or losses at the connect transfer. So all the three factors are there. So that's why it is about the all of the above. The system requirement needed in analyzing a link. What are the requirements? We require a transmission distance, that is the length of the line. Then we require a what will be the bandwidth, so data rate. And then we require a what will be the error. So that's why the BR. So all of the above the option, that is a D. Now in the link power budget, a link power margin is normally provided in the analysis to allow for a. Now whatever the link budget means what? Your system will work uh, for that much of a duration. Okay, or for a particular period. So that's why there will be a component changing. There may be a temperature fluctuation, or there may be a losses arises from the component that might be added at a future date. So that's why whichever the link budget we are defining, so how much will be the power at the detector. So that detector power may be because of the degradation of the compound, so it will be reduced. So that's why how much is the power required to be transferred from the transmitter side. So that is nothing but a link budget. So that's why the all of the options will be a correct. The total transmission time degradation of a digital link should not exceed. Now we can say here if we have a digital link, then we can say that the total time either we are using a NRZ or a RZ bit format. So if it is a RZ bit format, then it will be a 70%, and if it is a NRZ bit format, then we can say that it is about a 35%. So likewise, we can say that either it is a 70% or a 30%, 35%. So we can consider that it not be, it is either C or A if we have a RZ format or a NRZ format. Okay, you just modify. Next about a high impedance front end amplifier used in optical fiber communication system. Okay, in that case, we can consider that what will be the amplifier we are using. So now that amplifier used in a optical communication system, it has what will be whether it has low noise, low receiver bandwidth, or a large bandwidth. So amplifier it has a high impedance front end amplifier that has a low noise. Because of that low noise, that bandwidth will be reduced. That's why that low receiver bandwidth there. So that's why option C. The bit error rate is the ratio of what is the bit error rate? It's whatever we are transmitting the pulses in a particular period of a time, and we are measuring the error, how much will be the error in that particular period of a time. That's the duration there. So that is nothing but the what we can say that a bit error rate means what? Ratio of number of errors occurred over a certain period of interval to the number of pulses transmitted during that interval. That is the option A is correct. Then typical error rate for optical fiber system communication system ranges from what? 10 to the power minus 3 to minus 6, or minus 6 to minus 9, or 10 to the power minus 9 to minus 12. Generally, the typical system, if you see that we are using that 10 to the power minus 9 to the 10 to the power minus 12. Okay, so that's why that C 10 to the power minus 9 means what? We have the error in the system when we are transmitting a millions of a pulses. After that, there will be a one error. Means 10 to the power 9 pulses we are sending, and after that there will be a one error occur. So that is 10 to the power minus 9. That is a bit error. That optical amplifier used in what? Okay, both the cases, ultra ceiling, or we can say that it's a short link in a access network. So that's why the option C is the correct one. So an optical amplifier as a front-end amplifier for an optical receiver. So that is, we can say that optical amplifier as a front-end amplifier for an optical receiver. So whether it will be inline or pre-amplifier or a power amplifier. So inline optical amplifier means what? It is in between the line. So total length of the line supposed to be a thousands of the kilometers. So in between that, if it's supposed to be we are using the optical amplifier, that is the inline optical amplifier. So pre-amplifier, so that is before it, and power amplifier after that. Okay, so we can say that here front-end amplifier for optical receiver. So that's why we can say that a pre-amplifier before receiving the. That's why that pre-amplifier is the output. So power amplifier to boost the power at after receiver or after transmitter. So a pre-amplifier So we are using before the detector. Then an optical preamplifier provides a larger gain factor and a shorter bandwidth. So you can just, we are saying that it is in terms of a gain factor or a bandwidth. So if you consider that the optical preamplifier blocks, it provides a large gain factor, and why we are using preamplifier to provide the larger bandwidth. So that's why the option B, broader bandwidth and all. Then alloys of a semiconductor material such as phosphorus, gallium, indium, and arsenic, which makes up the active medium in. So now we are using the semiconductor material to develop the amplifier. So now which material? Right now it doesn't have any erbium rare earth component, so that's why it doesn't matter. Doesn't, it is not a B, iridium dope fiber amplifier. It is just like a semiconductor optical amplifier. Okay, that material belongs to the semiconductor optical amplifier. Then an erbium dope optical amplifier consists of, so if you see that it has a dope fiber, right? It has a pumping laser, pumping mechanism there. So for this particular pumping mechanism, it has a particular wavelength coupler, it has an isolator and a trap coupler to retrieve that information. That's why it is a all of the above. In erbium dope fiber amplifier, the pump wavelength is what? We can say that it is a shorter than the signal wavelength, or you can say that it is larger than the signal wavelength, or same with the signal. So if you consider that a amplifier, the pump wavelength generally it is to be larger than the signal wavelength. That's why option B is correct. Next one, in an erbium doped fiber amplifier, the reduction of gain occurs when the population inversion is. Now we can say that increase significantly by a large signal, be reduced significantly by a large signal. Okay, it is depending upon that is signal. So that's why if you see that, so that the reduction of a gain occurs when the population inversion will be reduced significantly by the large signal. So then in optical amplifier, the pump supplies energy to the electrons in what? Whether it is optical fiber or an active medium or a pump source. That is about the supply of energy to the electrons. That is in an active medium. So in an optical amplifier, it has a active medium. So that's why that active medium is to be used to amplify your optical signal. So that's why the option B is correct. The Raman amplification mechanism. If we see that Raman amplification mechanism, so that depends upon the scattering, or we can say that a scattered effect. Okay, light effect. So that's why there is no population inversion takes place. So that's why it is about the mechanism, Raman amplification mechanism, that is a without population inversion mechanism. So in wavelength division multiplexing, it is nothing but A, B, C, that is combine a number of independent information carrying wavelength on different fibers. Combine a number of independent information carrying wavelength on the same fiber. Because wavelength division multiplexing means what? We are combining a number of independent information, means different lambda 1, lambda 2, lambda 3 on the same fiber. So that's why that option B is the correct one. In wavelength division multiplexing, links require many optical sources with. So what about that link requires many optical sources with what? That is about a narrow spectral emission. Okay, so means different wavelength. So that's why the spectral emission band will be narrower here. Then WDM means wavelength division multiplexing transmission system consists of. So it has tunable light sources, or it has a tunable optical signal conditioning and a receiver. It has the both. So that's why that option C is correct. It has both the things, light sources as well as a optical signal conditioning and a receiving device. A WDM technique used in a long distance terrestrial and undersea transmission system. Then metro networks, fiber to premise networks. It is correct all of the above the option, because WDM network, it has a large bandwidth, large capacity, so that's why it is used to the all the applications here. Then a characteristic of WDM is that the discrete wavelength from an orthogonal set of carriers that can be A separated, without interfering with each other, B, rotate without interfering with each other, switch without interfering with each other, and D, all of the above. Now, if you see here, the characteristics that is of a WDM discrete from an orthogonal set of carrier that can be. It is same all of the above separated without interfering with each other because they are different lambda one rooted. So same fiber we are using, so that's why it rooted without interfering with each other and switched without interfering with each other. So that is all of the above because add drop multiplexing is there. So switching is there. So that's why it is all of the above option. A WDM network requires a variety of passive device includes whether it is split and combine or tap optical signal or tunable optical filters or tunable sources. Now here a passive device it doesn't require any source or anything else. So that's why splitting and combining it is occur in a passive. If you consider that a filter, so it is the active one. Tunable source it is active. Optical amplifier it is active. So split and combine or tap of optical signal that is a passive. So A is a option. So active devices that is the B option. In WDM performance of active devices provide. So now we can say that a device we are using, so active devices because they are working on the input and they are providing the output. Okay, so that's why it has a large degree of a network flexibility there. So that is a B now. Then 40 in an optical source term optical width. Optical width means what? We can say that it is regarding the whatever the spectral emission. Spectral. So that is in terms of what we can say that is about a spectral width lambda. But if we are just saying that in terms of a optical width means what? That is a frequency band occupied by the light signal. So that is about not a wavelength band occupied by the light signal. It is a frequency band occupied by the light signal. So generally we can say that generally if we consider that it is a frequency band occupied by the light signal, so then we need to explain the capacity in terms of whether it is gigahertz or terrain. So that's why mostly optical sources they have a spectral emission lambda. That's why it is about the wavelength band occupied by the light signal. That is a B. It's correct. Then in WDM standards developed by ITU specify channel spacing. Generally channel spacing that is in terms of a frequency, not in terms of wavelength. But in optical sources it is a wavelength. But in WDM standards developed by this ITU, so it is a channel spacing in terms of a frequency, not in a wavelength or a time. That's why that option A is a correct one. Then passive device operate in the optical domain. They can be we have the n by 1 n coupler that is because it just coupled the from n to n splitter power splitting takes place and power taps and star clips. So all of the above that option is all of the above. Then in optical domain passive component based on A optical fiber, B integrator optical wavelength, C bulk micro optics, and D all of the above. So now optical domain passive component based on all of the above because fiber is there, it has a different integrated optical wavelength, it has a bulk micro optics, so that's why that option D is the correct one. Then an end-to-end optical connection that passes through one or more intermediate node is called as because we are from one node to the another node. Signal propagating from one node to the another node. Here it is a light is propagating, so that's why it is about a light path, not light wave. Light is propagating from one, not light signal, not path. It is a light path. That's why the option B is there from node 1 to node 2. Okay. The component topology is used in optical network. So that is mesh configuration, ring configuration, star configuration. All the configurations use whichever the topology is used in a network. So all the top topologies are used here. So that's why that option D, all of the above is correct. Then in the link power budget analysis is a convenient method for what we have because power margin we are saying everything. So that is about that option B dispersion as well as that we can say that is sensitivity of a receiver. So that's why that option B is a correct one. So that is all of this MCQs of optical fiber communication. Thank you all of you. Thank you all.